If a drone had only one propeller, the entire body would spin out of control on its own. To prevent this spinning, you need to add a propeller at each corner. But if all 4 propellers spun in the same direction, the body would still rotate backward due to the reaction force. The solution is to have half of the propellers spin in the opposite direction. That way, the rotational forces on each side cancel each other out. So drones usually use an even number of propellers to stay stable in flight. This avoids spinning. The job of the propeller is to push air downward and create thrust. Motors mounted under the body drive them to spin. To precisely control the motor speed, you also need to adjust the electric current. This key device is the electronic speed controller, or ESC. A drone also has a tiny computer inside. It directs and coordinates the work of all the parts. So how exactly do the propellers make a drone fly? The key lies in the unique shape of the propeller. If you look at its cross-section, you'll see it's curved. When the propeller spins at high speed, this curved surface pushes air downward. According to Newton's third law, the air pushed down gives the propeller an upward force in return, which is thrust. Now, to make the drone move forward, we can increase the speed of the 2 rear propellers. This boosts the rear thrust, so the nose naturally tilts forward, and the drone gets pushed forward. Likewise, to fly sideways, you need to speed up the 2 propellers on the opposite side. So how do you make a drone spin in place? Notice that the propellers on the left and right sides spin in different directions. If we slow down the 2 propellers on one side just a bit, and keep or slightly speed up the 2 on the other side, the thrust on the left and right won't be equal. That unbalanced thrust makes the drone rotate. Now, when the total thrust from all the propellers added together exactly equals the weight of the drone, and all 4 propellers spin at exactly the same speed, wouldn't the drone just hover steadily in the air? In theory, it really should hover like that. But in reality, because of wind or a slight imbalance in the drone's own center of gravity, even if the propeller speeds are set the same, the drone might still drift a little. Once some outside disturbance tilts the drone's body, it must immediately increase the speed of the propellers on the opposite side of the tilt to correct the body back to balance. This adjustment has to happen very fast, and it has to be done over and over. Luckily, today's computers calculate fast enough to complete these balance adjustments smoothly and quickly. Moving on, we know that a drone flies thanks to its propellers, and the propellers are spun by motors. A drone uses a special kind of brushless DC motor. An ordinary brushed DC motor has brushes inside. When it spins, the friction creates sparks. At high speeds, it's harder to control. A brushless DC motor has no brushes. Its coils stay fixed in place. Only the magnets on the outside spin, so it's especially well suited for high-speed operation. However, this motor can't run directly on ordinary DC power. It needs a device to first turn the DC into an alternating power supply, something similar to 3-phase AC power. That device is the electronic speed controller. Basically, its whole job is managing speed. By changing the frequency of the current, it adjusts how fast the motor spins. So who gives the ESC its commands? It's a little computer inside the drone called the flight controller, or FC. It's the core control unit of the entire drone. This flight controller also has several sensors built in. There's a sensor that detects rotation. This lets the flight controller know how many degrees the drone is tilted. There's also a sensor that measures acceleration. It's used to tell whether the drone's speed has changed. These sensors are crucial for tracking how the drone moves and rotates. The flight controller also has a sensor that measures air pressure. The drone relies on this to figure out what altitude it's at. The flight controller and the ground remote control communicate by radio waves. They mainly use the high-frequency 2.4 GHz band. Because a drone needs to react extremely fast, the signal can't lag at all, so it has to use this high frequency. So when the operator sends a forward or backward command with the remote, the signal gets picked up by the flight controller. Then the computer calculates how each motor needs to spin, and sends the commands to the corresponding speed controllers. This is one of the most important jobs of the flight controller. Also, a drone uses a lithium polymer battery. This battery is lightweight, discharges fast, and can deliver a large current. Even if your propellers stop, it can still glide in the air for a moment. But if the motors stop, it crashes right away, because it has to keep pushing air down to support its own weight, and that requires a constant large amount of power. Lithium polymer batteries have high energy density and good discharge performance, which makes them perfect for drones. Many commercial drones are equipped with GPS. GPS can tell the drone its current position. To make a drone stay still in place, it first has to know where it started. The GPS signal is its reference for positioning. Even if it gets blown off course by wind or pushed by some other force, it can fly back based on its recorded position data. However, GPS isn't very accurate. The margin of error can range from about 1 foot to 30 feet, mainly because it doesn't receive enough satellites. To pin down your position, you need signals from at least 3 satellites. Simply put, the more satellites, the smaller the error, and the more accurate the position. Of course, besides GPS, a drone also uses acceleration sensors and other technologies to calculate its motion state overall, and then determine its position. GPS isn't very accurate at measuring altitude, so a drone has to use other devices too, such as an ultrasonic sensor or a barometer. An ultrasonic sensor emits ultrasound to measure the distance to the ground, but its measuring range is limited. It works fine at close range. For example, it uses ultrasound when flying at low altitude. When it flies higher, it switches to the barometer. Because of gravity, the closer to the ground, the denser the air. The higher up, the thinner the air, and the lower the pressure. The air in a sealed space expands as the pressure drops. The barometer works by measuring this change in volume to work backward to the altitude. However, air pressure changes with the weather. So before flying, you have to measure the current pressure on the ground first, as a baseline. Only then can you use the barometer to measure flight altitude. Also, during flight, a drone might hit an obstacle. So some high-end models come with cameras or radar for obstacle avoidance. But ordinary drones usually don't have this feature.